I want to say first, thanks so much to the organizers for this conference. It's really nice to see old friends here, so thanks for having me. So I'm going to be talking about eccentric nuclear disks around supermassive black holes. So it's a very different type of system than what Ram was talking about in the previous talk, where you have kind of like a cluster of stars around the black hole. And I want to specifically address tidal disruption events that I think should be prolific when you have these eccentric nuclear disks around your supermassive black hole. Here is a beautiful Spitzer image of Andromeda Galaxy. So this is dust. But zooming into the center, this is just a couple of parsecs. This is a Hubble image of the starlight, and you see this double nucleus, which you can get from an eccentric nuclear disk, but I'll explain that in one moment. So since this is a dynamics conference, I'm going to address why these eccentric nuclear disks are actually stable, and also why I think they're common in the universe. I will, of course, then address why we don't have one in our galactic center. Any theory that proposes they're stable and should be extremely common needs to address this point. And they'll move on to why tidal disruption events should be common with stars that originate from these disks. Talk quickly about the effects of GR, because GR, as we know, is kind of like the Achilles heel of a lot of secular dynamics. So GR doesn't actually kill the tidal disruption event rate coming from these disks, which is really nice. And then making a connection to E+A galaxies. And the reason I want to do that is because what we're finding with tidal disruption events is that their candidates are mostly occurring in very rare galaxies, particularly the optically selected TDE candidates. Something like 75% of them are coming from these galaxies that locally make up only 2% of the population. So these TDEs are coming from some strange, rare types of galaxies, and we want to be able to explain that. And I think I can make quite a natural connection to eccentric nuclear disks that could explain it. Okay, so let's just begin at the nucleus of the Andromeda Galaxy, since that's the best eccentric nuclear disk example that we have. This is a 2-parsec image taken with the Hubble Space Telescope, as I said. When this was first resolved, so originally the asymmetry of the nucleus was detected with Bloom-borne experiments, which I think the history of is really fascinating. But it took Hubble to actually resolve it into 2 peaks. And a very natural solution for what was going on in this nucleus was to say that one of these peaks, it's this one here, contains the supermassive black hole and the star cluster around it. And we just happen to have caught another star cluster merging with that central star cluster at a really good time. But if you look at the dynamical friction time scale, it would be really unbelievable to have just been lucky to catch this in our nearest galactic neighbor. So Scott Tremaine put out a paper in 1995 that explains really well what this structure actually is. So it comprises a single system of stars. They're all roughly the same age. In this disk, there is a caveat that there is actually another disk within this disk, and I'm not going to be addressing that in this talk, but somebody else will later in the conference. So this single system of stars is an eccentric nuclear disk structure, which means all the stars are on very highly eccentric orbits in quite a thick disk, but all of these orbits are collected onto one side. And so you might wonder, like, why would this be stable? Stars interact with each other. They want to spread out in phase space. The innermost orbit will want to precess, so will the outermost orbit. Why would they have exactly the same precession timescale? So what leads me to believe that this structure is actually stable, it's not just some strange transient system, is that it's not alone. And so if you took the Andromeda Galaxy and you moved it back to 5 megaparsec, which universally is not that far, Hubble wouldn't be able to resolve these 2 peaks. It would just be some kind of elliptical nucleus, and we see that a lot in the local universe. And there are many other galactic nuclei that actually show similar features, ranging from, let's see, I'm going to get this wrong. I think this is the brightest cluster galaxy. This is a low luminosity elliptical companion galaxy to M87. This, I think, is an S0 galaxy. So a lot of these galactic nuclei, when we're able to resolve them being particularly massive or particularly close, show similar features to M31. So I think these are common. We need to explain why are they dynamically stable. Eighth's not too buddy effects. I think it's secular dynamics that is calling the stability. Loads of people are going to be talking about secular dynamics, particularly Jihad Touma later on this week is going to give a review, maybe tomorrow morning. I just quickly want to say it's when you have a cluster of objects around a more massive object, you don't get random interactions dominating what changes the angular momentum of the orbits of these particles. You get, and it's kind of like a conceptual picture here, although you can actually do this computationally too. If you spread the mass of these stars out around its orbit, you can see that the gravitational forces build up over orbit after orbit. And these orbits can coherently gravitationally torque each other and change each other's angular momentum very efficiently. So it's this type of dynamical effect that I think keeps these disks together. A couple of equations. I'm just going to jump up here because I'm going to use them. The angular momentum of an orbit is given by r cross v. The torque, you would need to integrate all the forces acting on an orbit to get its net gravitational torque that's acting on the orbit to change its angular momentum. What I will do as a shorthand in this talk is just look at the forces acting at apocenter of the ellipse. That's where most of the mass is located if you spread the stellar mass out around the orbit. And that actually gives you a really good idea of how the dynamics is working. OK. There are two things we need to know for why these disks are stable. The first is that they exert these gravitational torques, and these are the two equations we need, very simple. The second is that circular orbits want to precess faster than eccentric orbits. This would be very intuitive if you think about eccentricity vectors all day. Short eccentricity vectors are easier to move around than very long eccentricity vectors. Well, one way to explain to undergrads and students you might be working with is to think of kayaks. If you're in a very short kayak and you want to turn 180 degrees around, it's pretty easy. You don't have to apply too much force or torque. If you're on a mile-long kayak, it's going to be a lot harder. You need a lot more to actually move your kayak around. So eccentric orbits need a lot more to actually get driven around. Circles are really fast. Okay, so those two things are all we need to explain in. So this is a very simplified picture. Just walk you through. This is your eccentric nuclear disk. The single black line is just meant to represent the entire disk with eccentricity vector pointing this way. And the net direction of precession is going to be in this direction, this prograde precession of orbits in this disk. If we pull an orbit ahead of the disk, we want to see what happens to it. And obviously, I'm going to claim the disk is actually stable, so you should expect that orbit to be tucked back into the disk. And that's indeed what happens. If you look at these two equations, the angular momentum of this red perturbed orbit is going to be, let's see, r cross v. Uh-oh, OK, let's try it. Oh, OK, 1 second. This is the angular momentum vector along the z direction of this particular orbit, because the star is moving like this around the orbit. You look at the torque it's going to experience. It's going to experience like a backwards gravitational force at apocenter against its direction of motion. So it's going to decrease its angular momentum or increase its eccentricity. When you increase the eccentricity, you're in a very long kayak, and it's hard to precess. And seeing as your disk is precessing in this direction, the disk is going to catch up with you because you slow down because of that gravitational torque that made you more eccentric. So this perturbed orbit gets more eccentric, it tucks back into the disk, where the disk basically catches up with it in precession. But what if it swings back around? What if it's too slow now? Well, then the gravitational torques reverse. Its velocity vector is pointing in this direction. The gravitational force from the disk is in this direction. It's very strong. It makes the orbital eccentricity decrease. And then you're in a very circular kayak, and you precess faster than the disk. So it's like a pendulum. You're just oscillating back and forward around the mean body of the disk. So what keeps it stable is differential precession, because of the different eccentricities, and the gravitational torques that change your eccentricity if you try and get ahead or try and move behind the disk. And so we see this in simulations very clearly. This is a very simple schematic. Well, it's a result of an n equals 1,000 simulation. We just look at two components of the eccentricity vector. We start off the disk very compact. but it naturally wants to expand out. The colors indicate some semi-major axis range in the disk. You should just kind of think the red is the real stable part of the inner disk. The blue orbits are the orbits that are on the very outside of the disk. And two-body relaxation actually can push them very far, so they're not really even a part of the disk itself. And they do their own thing. They actually precess retrograde. So if I just set this forward, what you might hopefully notice is this kind of rolling motion as the orbits are kind of going like this. Because this is eccentricity of 1 here, think this is eccentricity of 0.6. These are the eccentricity oscillations that you see in the disk that's keeping the orbits together. So it just keeps going like this. See, the blue orbits are just doing their own thing. They're ignoring a lot of this disk. Well, they're not ignoring the disk structure, but they're not staying up with it. So you get this kind of roll. Okay, I'll just stop it here. Okay. Hopefully there will be a John McGrain. Hopefully there will be a talk by John McGrain. Thanks. About the structure of the M31 nuclear disk. So I just want to say what we get from these simulations is you get a decreasing eccentricity profile as a function of radius. So even if you start off with a flat eccentricity profile in your disk, you always get this decreasing profile. They're innermost orbits because they feel a stronger stellar density because we put in a disk that drops in surface density as a function of radius. Their innermost orbits want to naturally precess ahead of the disk initially, and precessing ahead of the disk torques you to higher eccentricity. So the equilibrium structure of this disk is always that you have high eccentricities for small semi-major axes, and you drop down. So that's actually seen in M31, so it's nice that this actually makes sense in this model. Again, these bins out here are these flung out from two-body relaxation orbits that are just doing their own thing and messing up everything here. This is very important for the TDEs, or the tidal disruption event rates, because you start off with a flat eccentricity profile, but your disk naturally wants you to make your innermost orbits more eccentric, and then your perturbed orbits oscillate in eccentricity. So those innermost orbits are really in danger of getting too close to the massive black hole. And so this is what we see in our simulations. This is log axis of 1 minus eccentricity. So eccentricity up here is 0, and it goes down to 10 to minus 7 here. And this is a function of time in units of orbital period. So for M31, this would be a few million years here. And so what we find is that these innermost orbits, when they're oscillating, they go to really extreme eccentricities. I had anticipated down on paper this would be an oscillation of 0.2 to 0.6, and would be very happy in eccentricity space moving around. But the torques from the disk are so strong that they regularly go from 0.2 to 0.99999 and keep doing this. And so in my code, I don't have a tidal disruption radius. The orbits are allowed to go through an eccentricity of 1. But you can see that these events here, a real star would not survive the passage so close to the supermassive black hole. Very quickly, I gave a similar talk about a year ago at a conference in Fabio Antonini, wherever he is here. You asked me about general relativistic precession, saying, this is a lovely mechanism, but GR is going to kill your event rate, absolutely destroy it. And I haven't actually mentioned what the event rate is. It's shockingly, ridiculously high. I'll maybe mention it later, and you can just not believe me. So I have a graduate student who over the summer looked at general relativistic precession, and her first answer was compared to Newtonian simulations and general relativistic simulations, there's no difference with the event rate. And I was like, okay, well, it's your first project. Try again. Like, tell me it's reduced. You know, now it's only a factor of like 10% or something like that. But she was correct. So the expectation was that GR precession, once you get to a high enough eccentricity and you're in danger of being tidally disrupted almost, you're also so eccentric that you should just swing away from the disk really fast, because of general relativistic precession just launches you ahead and away from the disk. So the torques won't be pushing you to the highest eccentricities. So what Heather found is actually the torques from the disk are so strong that you're essentially in an empty loss cone regime. And those secular torques from the disk can push you from below the loss cone straight to an eccentricity of 1 in less than an orbital period, which we see here. This is a tidal disruption event, which ER. Just some comparison of the torques here. Don't want to spend too long on this, but she's writing this up. OK, a link to E+A galaxies. We're seeing all these tidal disruption events happening in these really rare galaxies. So what is going on? So eccentric nuclear disks, at least in the simulations, are producing something uncomfortably large, like 1 to 10 per year. Initially, in these disks, yes. Yeah, it's not really believable, but that's what we're getting. And we're seeing tidal disruption events in these post-merger galaxies. So what is the link? Hydrodynamic simulations by Elliott Quattard and Phil Hopkins have found that when you have gas-rich major mergers between galaxies.
Is it known that K+A galaxies are post-merger? Or is it coolant flows?
In the literature, people are pretty.
In the local universe, it's an interpretation of post-merger.
Right.
Yeah, because in the higher redshift, A plus E galaxy actually the galaxy that plunging into the cluster of galaxies. So before they have merged into the central galaxy.
So a lot of these E+A galaxy and K+A galaxies show evidence for recent mergers. There's a E+A galaxy that actually shows evidence for a merger, and another merger is actually happening on top of it. So it's an interpretation right now, but I think it's fairly secure. So this is what I'm going on right now, and this is how I would link it up. If it's something else, this wouldn't hold. So what they find in their simulations is the gas-rich gas-rich major mergers produce eccentric nuclear disks. And how they do that is the two supermassive black holes find each other in the center of this merger product. They scour out of a core of stars in the center. The nuclear star clusters are pretty flattened. A lot of stars get thrown out. And then subsequent gas flows inwards produce this eccentric disk structure that is stable. It processes prograde, but it's actually very important to have that scouring out of the core for this to be stable. So if this is true, and a lot of these eccentric nuclear disks actually formed in this way, and K+A galaxies are indeed post-merger galaxies, this would explain why we're seeing so many tidal disruption events coming from these particular types of galaxies. They contain eccentric nuclear disks, and they're very efficient drivers of tidal disruption events. It's a very cartoon timeline that I have here. You get a merger product. You've got an eccentric nuclear disk at the center. This is not real data. This is tidal disruption event versus time. This is my overall picture, and this is what I'm trying to understand here. All very controversial things I'm going to show on this made-up plot. What does a 1 TDE per year or every 10 years actually look like? Would you be able to distinguish it from an AGN? I think it would look different, perhaps, but it's not totally clear to me how. As the rate drops, and I'm running out of time, but why the rate would drop. If in isolation you have your eccentric nuclear disk and you're putting stars into the black hole, you're getting rid of mass. You have to conserve angular momentum. And so your disk should become less and less eccentric very slowly until the innermost edge, even though it is more highly eccentric than the outermost edge, during its oscillations won't get high enough to be tidally disruption stars anymore. So your rate should be decreasing with time if it's an isolated disk and more stars aren't being added to the disk, and that's a mess. I don't know. But maybe in that in-between phase, you're going from something that looks like an AGN, but every now and again you throw in another TDE. What does that look like? Changing look AGN? I don't know. Eventually, you'll pass through a K+A phase post-merger. Your rate's still really high. And the evidence for this, it's really, really early days in tidal disruption events right now. But what kind of supports my made-up cartoon is that there is a controversial claim that we've seen a tidal disruption event candidate in a Euler galaxy, a very recently merged galaxy. And they were only looking at 10 such galaxies, and they found one, and so they came up with an event rate of something like 0.1 per year. So highly controversial, but extremely high event rate. Something very strange is going on in this galaxy. Whereas with K plus A galaxies, the rate is something like more of 1 every 1,000 years. So you'll see if we put a point here and a point here, it's proven that this cartoon picture works. Okay, some predictions from this would be, obviously, if you can resolve these nuclei, they should look like M31. Not necessarily a double nucleus. If you see it from a different line of sight, you might get just an offset nucleus or something else like this. But they should host eccentric nuclear disks if this is correct, or if this is explaining why we see so many. The TD rate should decrease with time, and also the type of star that will be disrupted will get older if it's all these stars that are formed in one burst in this disk that are getting disrupted. There could be background stars, and that's kind of interesting then for like MRIs and things like that. I just want to leave. Oh yes, I want to say Nick Stone is going to be talking very soon, and so he has different ideas about how to explain this association with TDs and K plus A galaxies. I think I'll just like leave these final thoughts up because I'm running out of time.